Hi there, welcome to our channel where we talk about traffic operations in practice. The overall intent of this video series is to reduce the learning curve for students and entry-level engineers by providing them free and high-quality learning materials in the field of traffic operations, including highway safety and travel demand modeling. The majority of content in this work is written by Professor Jiangling Wu. My name is Amit Kumar Singh. I'm one of the contributor of this work. I'm a licensed engineer in the state of Texas. I received my bachelor's from IIT Bombay in India and my master's from UT Austin in US. Other three contributors of this work are Priyanshu Singh, who works in the field of artificial intelligence, Nidhi Kumari, who has a background in computer science and is a programmer, and Namrata Kumari. She has a background in electrical engineering and currently she is working as data scientist. Now let's get to the main content. This is going to be the last and very important video for travel demand model. Here we will discuss the output processing. In previous video, we looked at how travel demand models are built and used and calibrated, and then uh, at the end of previous steps, what we got was a link flows on for the future years. So we have link flows. If I can type here, link flows for the horizon year. So at the end of previous videos, we are up to here. Now we can take this link flows and we can use it as it is, or we can have some adjustments based on this link flows. So we will look at how we use the TDM output for the future year, which is the link flow for the future year, to generate actually the final volume. So often the output flows produced by TDM is inconsistent with expectation. This is an understatement. Most of the time the TDM output is not good, to say the least. So the TDM output is generally far away from what we are expecting. So what we do is we try to adjust it the best we can based on the how the existing TDM output was. We try to adjust the future TDM output as well. So horizon year peak hour count traffic volume are developed based on TDM output and expected traffic flow during horizon year. So this part is where a lot has been said in this statement. So future traffic volumes are developed. So once we get the link flows, we usually get for AM peak period, and we have gone through the discussion of peak period versus peak hour, and this peak period link flows are then used to generate AM peak hour traffic, peak hour volume, peak hour volume. Now the is based on this link flows and also expected traffic flow during horizon year. So like I mentioned, the TDM output is usually a little bit vague, and it's usually away from what we are expecting. So what I personally try to do is I look at the study area as a whole, and then I look at individual TAZs. Then the first thing I try to do is figure out the growth factor, employment and population growth in the study area. So let's say these are different TAZs in the study area. I'm drawing too much. So first I try to see what is the growth in the area, and let's say I'm drawing this roadway network. So let's say these are some of the roadways in the study area going like this. So first I try to figure out, usually the roadway networks are along the boundaries of TAZs. So it would be something like this. Uh, First we figure out the growth within the TAZ. So let's say the growth here is 5%. Then I kind of intuitively know that the link which is nearby this TAZ will experience a growth close to 5%. Let's say growth here is 4%, growth here is 1%, growth here is 2%. So based on population and employment growth, I try to picture at a bigger level in my mind. I try to picture where those growth areas are, and then based on the select link analysis, I try to see where those volumes will go. And like just looking at the overall travel pattern based on the population growth in the area and employment growth in the area, and running several select link analysis, we can understand the travel pattern in the existing network, and we can understand the growth that we are expecting. So using select link analysis or using OD tables, I try to understand where the volumes are coming from, where they are going, and where the growth is happening. So if growth is happening nearby a certain roadway, then I'm expecting the volume near the certain roadway to go up. Then I also in my picture, I know where those volumes are going and how they are going to get distributed. So overall, what I try to do is I try to capture a future picture for myself without running the TDM. So let's say I'm working on a project, and without running and calibrating, doing anything, what I try to do is try to figure out what are the growth areas, which zones are gonna have higher growth, which zones are gonna have lower growth. Then I try to understand the trip pattern within the study area by using OD table and select link analysis. Now I have an understanding on how the travel pattern is within the study area and how the growth is gonna be happening. Then in my mind, I have a picture of how the future trip pattern will look like. So if there are more growth in certain zones, then there will be more trips going to and from those zones. So in my mind, I try to picture all these things and then try to come up with a crude estimate on how much traffic volume will be there on the future links based on the growth rate I have in the mind. So this kind of helps me towards the end of the project when we got the uh, future link output, and some of them make sense and some of them does not. So that mental picture helps me kind of uh, use my engineering judgment to adjust some of the traffic volumes through intuition, and also for me to kind of have a cross check. So if some of the volumes are pretty high, then I know intuitively that okay, I was not expecting this high volume, okay, I was expecting this volume. So the first step of travel demand model, I would say for engineers would be to have an expectation on what the future volumes is gonna look like. So we can build our expectations based on the growth rate in population, growth rate in employment, travel network changes, and running the bunch of select link analysis on the network to understand where those where which ODs are going through certain links, and then looking at the ODs. So this mental picture will help us kind of form our engineering judgment on which numbers to adjust, and those are engineering judgment plays a very big role on producing a high quality forecast compared to just taking the TDM output, which is for most part in my personal experience throws some weird numbers, and we need to be careful about using the TDM output directly. So having that intuition, uh, having that kind of engineering judgment kind of mind, having those numbers set in our mind is gonna help us to adjust the output numbers. So that's kind of a thought process I usually use, which helps me kind of try to finalize the future volumes. So traffic volumes are also adjusted to balance the forecasted traffic and refined based on other considerations such as directionality, which we will discuss soon, volume consistency of complementary movement, and during AM and PM peak hours, and we will discuss all these things very soon. So the first process we use is to calculate the correction factor if needed. So let's say I'm looking at an area where in existing the travel demand model forecasted a volume of 1000. However, in practice, we know the volume was 500. So this is what travel demand model forecasted for existing, and this is uh, what we observed in field. So let's say we did all the calibration and this anomaly cannot be fixed. So what we can do is we can assume that this anomaly is gonna be there in the future, and we can adjust these numbers based on the either the difference method or ratio method or combination of both. So in this case, since this number is high, I would use the ratio method. So let's say my future volume for this particular location in future, I'm forecasting 2000 in TDM. Then using ratio method, I will actually use just reduce it by half. So I will reduce it by half and make it 1000 vehicles. So in existing, I will have 500 vehicles. In future, I will have 1000 vehicles. So this is to calculate the correction factor if needed. In most of the projects, we do need the correction factors. Then second one is peak period to peak hour conversion. So when we get the TDM output, we get the period peak period output. Then there are usually a factor which we develop based on existing count, which converts the peak period to peak counts. So looking at existing peak period versus peak hour count, uh, HOUR. So looking at existing peak period versus peak hour, we come up with a factor, let's say usually like 2.3 or something for 3 hour period, which converts peak period to peak hour. Then we multiply, then we divide all the peak period numbers with this number to get from peak period to peak hour. Now once we change from peak period to peak hour, the volumes get unbalanced. Before discussing the unbalanced volume, once we forecast the final volumes, because there is uncertainty involved in the future forecast, we round up the final number based on table 3.5. So in one of the videos we were discussing how the rounding works for future numbers, and this is one of the guidelines taken from, think is from my favorite DOT guideline, F dot, as I think so. So this is most likely taken from F dot on how to round the final numbers. So first we try to see whether the adjustments are needed on link by link basis, and then we convert the peak period to peak hour, and then we round it up, and then we do something called turning moment volume estimation. So in previous videos, I mentioned that the TDM output usually gives the link volume. So at an intersection, we will know how much volume is entering, how much volume is exiting, how much volume is entering in southbound direction, how much volume is exiting in northbound direction. Similarly, how much volume is entering in northbound, exiting in southbound, entering in eastbound, and exiting in westbound direction. So we know all these volumes. There are 8 volumes we know, and we are trying to predict the turning moment count. So left through right, and then left through right, left through right, left through right. So we are trying to predict 12 variables using 8 equations. Now, as we have seen in the trip distribution, when the number of variables are higher than number of equations, there are infinite set of solutions. So this turning moment count equation coming from travel demand model always has depending on number of legs, if there are 4 legs, has infinite set of solutions, similar to the trip distribution method. So what we can do is we can actually reduce these equations similar to trip distribution. So in the figure on the next page, these are turning moment counts which we are trying to estimate. Those are given in black color here, and the TDM output is given in blue color here. So the blue color is what is known, and the black color is what we are trying to estimate. So what we can do is we can convert them into equivalent matrix, where we are trying to estimate this black color matrix such that the TDM in and TDM out, TDM in and TDM out are matched. So looking at this matrix, it looks almost exactly similar to what we were trying to do in trip distribution. We had almost same matrix, and there are 4 different methods to come up with a come up with this number such that it matches the rows and columns. So we looked at the average growth factor method, freighter method, furnace method, and optimization method. So we can use either of four. I highly recommend to use the optimization method, but we can use either of four to solve this problem. Now when we solve this problem, there are, like I mentioned, there are infinite set of solutions, similar to trip distribution. So in trip distribution, what we had was a base OD. So here what we have is called base turning moment count, base turning moment volume, let's say. So here what we have is base turning moment volume, which is an estimation of future volumes. So usually the base turning moment volume is what we see in existing. So in 90% of cases, we set the base turning moment volume as same as the existing turning moment volume. So existing turning moment count. So we just take the existing turning moment count and take the link flows and try to match the link flows as well as try to match the existing turning moment count. However, when I was talking about intuition here, if from my intuition I know that there are gonna be development such that the left turns will be heavy in future. For example, let's say I have a roadway network here and there are more developments in future in this area and there are more developments in future in this area. Then I kind of know from intuition, which I was talking about, that there will be more trips going like this. And similarly, there will be more trips coming like this. So I know that in future, this left turn proportion will go up. And this through and right turn will also go up, but the left turn will go up more because there are developments here, assuming that everything else remains constant. So from intuition, called engineering judgment, what we can do is we can try to guess. Uh, we can use the engineering judgment to generate desired turning moment volume ratio. So what I can do is I can override the existing turning moment count here. So let's say in existing, this left turn is 50 vehicles. This through is let's say 200 vehicles, and this right turn, let's say 500 vehicles. If we use the existing turning moment count to forecast the future, then we're gonna end up with uh, let's say the total volume here is, so right now the total is 750. Let's say in future this number is gonna bump up to 1500. So if we use the same existing ratios, then we will end up with this number 100 here, this number as 400 here, and this number as 1000 here. However, from my intuition, or call it engineering judgment or select link analysis or trip pattern, I kind of know that this bump in traffic is more to allocated towards this left turn, which will also be actually reflected in this trip going out. So this trip going out will increase, so number of trip going out will increase, and which will kind of help us to bump this number. But irrespective of that, when we are trying to take a guess on how much proportion this will be, so what we can do is we can allocate more weightage to this left turn and let the optimization algorithm try to fit this 1500. So once we run the optimization, this number may bump up to, let's say, 150. So 3 times of what it is currently now. And then this is 100. And this one may be only 350. And this one may be 100. Sorry, this was 500. So this is 1000. So let's say this is 1000. So now we have, if we would have gone with existing data directly, we would have end up with 100 left turns here. We used our engineering judgment to kind of ask optimization algorithm to bump up this number more, give a little bit more value to this left turn, because we know that there are developments that has produced this left turn more in the future. It will also be taken care with this outflow a little bit up to some extent, but not completely. Again, there are infinite set of solutions, and this minor increase might be adjusted to some other moment. So what we can do is we can adjust this in the optimization such that this number goes up, and that's how we kind of forecast the future turning moment counts. So what we have here is we have the TDM output for both directions. We convert them into equivalent matrix estimation, and there are four methods to solve it. And like I mentioned earlier, one of the best method is optimization, which allows us to play around with different ratios we wanna kind of put in. So in existing this was the ratio, but in future we know that maybe left turn will be higher, so we can bump this importance of this ratio up and let the optimization give us the final solution. So that's the turning moment count estimation. We don't usually do it by hand. There are Excel sheets we set up, and once we do it for one time, then it's all about engineering judgment on where we want to give more weightage, and the Excel sheet takes care of everything. So just for the calculation, it seems confusing. However, when we implement it in Excel, it's just one time thing, and then we focus more on the engineering judgment side, and the Excel takes care of everything else. So far in output processing, what we did is we corrected the link flow if needed using difference and ratio method, which was here. So what we did is we looked at how the existing TDM was behaving, and then we corrected the future TDM. Then we converted the peak period into peak hour, and then we took the link flows and changed it into turning moment counts. So in the output now we have the intersections with all the turning moment counts. Then there is something called volume balancing. Volume balancing is the final refinement where we adjust numbers such that they are consistent with each other. So volume balancing usually finds a lot of errors. So at this stage, let's say I have in volume balancing stage, we usually find up to 30 to 50% of numbers being wrong. Let's put it that way. So this is kind of an important step for final check. So volume balancing and final turning moment volume refinement. So if any correction in step 1 are made, then freeway volume get unbalanced, and then we balance them out. Freeway volumes are balanced in such that total traffic upstream and downstream of a ramp is always equal. So I have an example here which shows the example. So let's say we have 1000 vehicles here and 300 vehicles are exiting. Then number of vehicles left here will be 700. Then there are vehicles entering here 500, so number of vehicles here will be 1200. And then 1200 minus 200 is 1000, and 1000 plus 100 is 1100. So when I'm trying to put the volumes after peak hour changes, these volumes may not be balanced. So instead of 700, I might have a number as 750. Then either I need to adjust this ramp number or this main lane to make it work. So that's the freeway volume balancing. A lot of volumes adjustments are made at this level. So additionally, if the traffic volume in between the intersections are also balanced as a standard practice. So if we are looking at two intersections, well, if we are looking at two intersections, so let's say 100 vehicle is coming out of this intersection, and 200 vehicles are approaching this intersection, which can happen because let's say there was a CC connecting here. So what we do is either we balance them out, so either we bump some of the numbers such that this one becomes 200 uh, or this one becomes 100, or what we do is we put a major state depending on how much is source and sink. So if this volume difference usually is greater than 50 vehicles per hour, we usually put a source and sink. If it's less than 50, then we adjust it in the turning moment count. So in this case, we will actually put a source and sink, and so okay, there is a major driveway here, assuming that there is a major driveway. If there is no major driveway, then some of the numbers either on this side or both needs to be adjusted. So there is a lot of judgment, a lot of playing around with numbers, and a lot of adjustments involved in finalizing the final volumes. And then there are some checks we do. Those checks are here. First one is growth rate checks. So what we do is we looked at the existing roadway network uh, throughout the study area and figure out how much traffic has grown from existing to future. Let me reload this. I'll reload this soon. So we try to figure out how much traffic has grown from existing to future at important lengths. So let's say growth rate here. Uh, we compare traffic count here and here. So this is my existing counts. COUNTS. So we compare with existing count of future hourly volume. Hourly volume. HP is usually reserved for heavy vehicles, but let's call it hourly volume. So we compare these two numbers and try to figure out what is the growth rate. Then we try to compare these two numbers and try to figure out what is the growth rate. Then similarly, uh, we look at the exact location in future and try to figure out what is the growth rate. And based on our engineering judgment, we have some sort of idea on what kind of growth rate we are expecting. So we looked at the population growth rate, employment growth rate, and overall growth rate in the area or the nearby area in general, and we kind of have an idea of what is the expected growth rate range. So let's say expected growth rate range is between 2 to 5%, and we see a dramatic increase, let's say 15% growth here, then something is off. Then we go back and look at the model, or if it's a little bit up and down, then we try to adjust it. So that's the growth rate check. A lot of errors are found when we are playing around with growth rates, and we see some of the links are unrealistically high because the travel demand model has thrown some weird output. Second one is directionality. So AM and PM peak traffic volumes have directionality associated with them. Let me reload this real quick. So in AM peak, if one direction is peak and the other direction is small, so this is my AM peak. In PM peak, usually the opposite happens. So this direction will have less vehicles, and other direction will have more vehicles. So this is called directionality. If if a direction has more vehicles during one peak hour, then opposing direction would have more vehicles during other peak. So this is called directionality, and what we do is we try to calculate the directionality factor here. So let's say directionality factor is 0.5, and in PM if we come up with directionality factor uh, let's say 0.57, if the directionality factor is let's say 0.85, then we may think that something is off. uh, a a closed system typically tries to maintain the directionality. Even though there are more vehicles in PM, in general the directionality kind of remains the same between AM and PM. So we try to figure out the directionality in AM, then we try to figure out the directionality in PM and try to see if there is a big difference between them. If a big difference in directionality is found, that kind of indicates some error in the travel demand model. So that's the if D factors are significantly different between base year and horizon year. Okay, so also we try to compare the directionality between existing year and horizon year. So let's say directionality in existing year is 0.57. So we calculate the directionality for horizon year, and let's say this is horizon year, and directionality came out to be 0.75 or something. Then we know that in existing the directionality was low, but in future the directionality is high. Then we go and explore if this high directionality is warranted. or the other way around. In AM, if there is high directionality and in future there is low directionality, then we go and explore whether this directionality is warranted or not. So usually we try to compare directional volume during AM and PM within the same year, and then we try to compare the individual peak hour between current year and future year to see if the direction has changed significantly between the base year and future year. So a lot of errors are found when we are looking at directionality of the volumes. And the last one is complementary turning moment count. A lot of errors are found when we are looking at complementary turning moment counts as well. So what is complementary turning moment count? Going up. So complementary turning moment count is this. Let's say 100 vehicles are going in morning peak, are taking right. Then by the complementary moment kind of logic, if 100 vehicles are turning right in the morning peak, in evening peak the number of vehicles turning left in the opposite direction should be closer to 100. So let's say 1000 vehicles are turning left here in PM peak. That kind of is a red flag that in AM peak 1000 vehicles are turning right, but where these vehicles are coming from, that 1000 vehicles are turning left in PM peak. So the top part we are looking at AM peak, in the bottom part we are looking at PM peak. So what we do is we looked at the complementary moment. So in AM peak, this right turn is complementary with this left turn. I should probably draw them with different colors. Similarly, um, this left turn will be complementary with this right turn here in PM peak. Using another color, let's say this through here will be complementary with this through here. I will run out of colors soon. This left turn will be complementary with this right turn, and we get the picture. So what we try to do is we try to see if the complementary movement volumes between AM and PM peak are close to each other, or whether they make sense or not. In most of the cases, because the TDM output is so weird and there are infinite set of solutions, again this all of these issues occurs because usually there are infinite set of solutions that satisfies certain criteria we are trying to define in travel demand model. So the output we are getting from different methods might have put this as a very high number and this as a low number, because since there are infinite set of solutions, uh, it might happen that all the conditions are still satisfied, such that this number is pretty high and this number is high and this number is no. So now we do this complementary turning moment count check, directionality check, growth factors check to see whether we have unrealistically put some number high and some number very low. So these are some of the common steps of post processing which we typically do. There are some other checks we do, and these are some of the major checks. So if any changes are made during the checks, then the traffic volumes are rebalanced, and final set of balance volumes is the output of traffic volume forecasting. So after all the checks are done and completed and the volume kind of makes sense, those checks are growth factor, directionality, complementary turning moment counts, and then volume balancing for freeway. After all the checks are done, then we finalize the traffic volumes, and that would be the output of traffic volume forecasting. So let's look at one of the examples I have here. In the example I have we have this freeway with existing counts. Let me reload this page again. We have this freeway with existing counts. So these are the existing peak period count. Then we have existing base year peak hour count. So this is peak period count, this is peak hour count, this is existing TDM output, and this is future year output. So when we are running the future year model, all we get is this number, and these information are there for us, these two are collected, and this is from TDM output. So based on the existing information, let's correct this final number which we got from TDM. So the first thing is calculate the correction ratio using a ratio method. So first we need to figure out what is the correction method we are going to use. uh, what is the correction ratio we are going to use. So what we will do is we'll take this peak period and compare with the TDM peak period and try to figure out the correction ratio. So the count is 1000 and the TDM output was 800. So the correction needed to go from TDM output to count is 1000 divided by 800. This is kind of a correction needed to go from 800 to 1000, and this is equal to, I have put here 1.25. Now what I can do is I can take this number and then multiply with 1.25 to move from TDM to kind of the actual counts. So I have the correction factor here 1.25. Let me calculate just one more. So TDM output here is 300. However, in existing this was 200. So the correction factor for this ramp, usually we calculate correction factor individually because of a lot of complications going on in the system. However, we can also calculate one correction factor for a small area. So here the correction factor to go from 300, which is the output, to 200, which is the what we observe, is we're gonna take this 200 divided by 300, so is 2 by 3. This is the correction factor. So now we have 1300 here. If we want to convert it into what we are looking to observe, so this is the output, and if we are looking to observe, so it's 2 by 3 into 1300, whatever that number is. So it's around 850 something. So this is the adjusted number 867. So in the first one we had 1.25, then we multiply with this one, then we got 2500. That's how the corrections work. Then the second one is adjust the AM peak period traffic volume during horizon year using the ratio method. So first we calculated the ratios, uh, then we determine the uh, future volumes using the correction. So determine adjusted AM peak period traffic volume. So this is the adjusted. Now the third part is to calculate adjusted AM peak hour traffic. Now we are trying to convert period into hour. So usually we have a single conversion factor to convert peak period into peak hour, but here, since we have a lot of data, what we can do is we can see uh, in AM peak period here there was 1000 vehicles, but in peak hour there were only 400. So first we can uh, okay, there is a single factor which is given as 2.5, so we don't need to calculate, we don't need to figure it out what's the ratio of this and try to adjust it. So usually a single correction factor is used, or a single factor is used to convert peak period to peak hour and peak hour to peak period. So what we are gonna do is we're gonna take this number and just divide it by 2.5. So this is peak period and divided by 2.5. So 2500 divided by 2.5 is 1000 vehicles, and 600 divided by 2.5 is 240, and so on. So so the first one is correction ratio. Correction ratio. The second one is adjusted future. Adjusted future peak period. Peak period volume. Then we have adjusted future hourly volume, or peak hour volume. Hourly volume. Since we always report the hourly volume, so we converted the travel demand model peak period into peak hour here. After we got the hourly volume, then we are trying to calculate the growth rate. So the way to calculate growth rate is, let's say the existing base year is 2020 and the future is 2050. So we have 30 years. We have 30 years in between. So in existing, the count is 400 vehicles here, which has gone up to 1000 vehicles. So in existing, this number is 400 in 2020, and in future in 2050, this number is 1000. So we can calculate the growth rate here, annual compounded growth rate. So annual compounded growth rate here will be simply the final this final number 1000 divided by existing number 400 to the power 1 divided by n here is 30 years minus 1. That's the growth rate. So if I can open my calculator and Excel, so I just calculated it in Excel and it's 3.1%. So similarly, we can calculate the other annual compounded growth rate. Now, after calculating the growth rate, is asking if the expected growth rate is between 2 to 4%, then identify any growth that is not within the expected growth rate. So here we have two growth rates, 5% and 0.9%. This is way too low and this is way too high, which is not expected. So either we can, first we will go and look and try to figure out why these numbers are high and this number is low, why these numbers are not as expected, and after a lot of trials, if we cannot figure it out, then we will adjust it such that the freeway are balanced. So during freeway balancing, we will, if we cannot figure out anything, then we will probably lower this number and move this up to balance the freeway. This is the last page of chapter 3 of travel demand model. Kind of wanted to end the video and the chapter with some lesson learned from our experiences working on travel demand model. The first experience is traffic volume forecasting is one of the most complex and crucial part of traffic operations. Depending on what volumes we are predicting, the future is kind of set. The future for traffic operations, future for roadway design, and a lot of things are set based on what volumes we are trying to forecast. So traffic volume forecasting errors can lead to traffic analysis and roadway design errors. So at a later stage, if we find out some of our numbers are not consistent, then we have to revise our roadway design and traffic analysis. So it's very important to give focus on traffic volume forecasting and try to finalize a number that is consistent, that is what we are expecting, and that is consistent with models. So that's first one is about the importance of traffic volume forecast. Is very important because it lays the foundation for future work in traffic analysis and roadway design. The second one is, when should we call stop to the calibration? So oftentimes engineers are caught up, including myself, in adjusting TDM to improve its output. Since TDM can take several hours to several days to run, this can easily spiral into a lot of project time. So what happens is, once we change one thing, we feel that everything is gonna be fine. Then when the output comes in, then we face something else is wrong. Then we try to fix that one, then something else comes out to be wrong. So when we try to fix one thing and we are pretty sure in our head as an engineer that we have got everything right, something else comes up a little bit off. And we try to keep adjusting it until everything is perfect. So in most of the projects, what it does is it takes a lot of project time and we might not end up with a good reliable result because there might not exist a solution, or TDM may not be the best way to approach it, or a combination of many other factors. So when we are working on travel demand model, one advice would be uh, to have a timeline set. So it's a good approach to try to make TDM better to generate reliable output, but a timeline should be set so that we do not overrun and uh, become crazy about finding a perfect solutions, because there may not exist one. So let's say we spent 3 weeks on TDM, and we came up with one output which kind of looks good. Then we can easily spend like 3 months and still not have a much of improvement over the existing. So we should be little bit mindful of the time, because as an engineer we try to overthink and we try to make everything perfect, but TDM is a messy topic, and we should know how much time is allotted to TDM. We can easily spiral, it can easily spiral in a lot of project times. The same thing goes for other calibration we do for traffic operations. For example, vision calibration, we try to think that the next change is gonna fix everything and something else messes up. So this happens very frequently. We need to know where to kind of stop when we are trying to calibrate, and we are not trying to make it over perfect and then we spend months and months with no improvement at all. And the third one is TDM is not known to generate reliable traffic flows because the TDM models are built on a lot of assumptions. However, if the traffic volume forecasting is very important, so we cannot get passed by. So it is important to check for the final traffic volume for consistency. Oftentimes the growth rate for several links are erratic and unrealistic. So we'll looked at several checks. One was growth rate, one was directionality, one was complementary moments. So at project beginning, this one is talking about the our intuition, which I was trying to explain. So in the project beginning, what I typically do is I look at the study area, look at the growth, and look at the trip pattern and do the select link analysis, try to figure out how traffic is flowing in the study area from zones to zones and how those zones are going to evolve in future based on the employment and population growth. Then I try to predict in my head on how the trip pattern will change in the future without the travel demand model. This kind of intuition gives me kind of an estimate of traffic volume that we are looking to generate. So an estimate of uh, future developments can be made based on population and employment. Based on this information, engineer could anticipate the future traffic flow pattern and prepare a rough traffic volume estimate. So either in my head on a scratch paper, I prepare a rough traffic volume estimate without running TDM. This kind of helps me later on when the TDM outputs are sometime good, sometime not good. So usually just by looking at the basic information of the roadway structure, roadway improvement that are gonna be there, how much uh, how much development are gonna be there in the area, and which volumes are going to increase and which volumes are going to decrease. I kind of prepare a rough volume estimate without running the travel demand model, and then I run the travel demand model and try to see how far off travel demand model outputs are so when I come up with a final number, I try to see whether they are consistent with the rough estimate I had. If they are if they differ significantly, let's say more than 25%, then I try to give a closer look to the travel demand model on whether whether I missed something or something was off. It's kind of some uh, some lesson learned we wanted to share. So the first one is the first one is TDM being very important but very complex. Second one is uh, uh, not getting caught up in a spiral of trying to fix TDM models. So we should try to do our best, but we should set a timeline. Otherwise, we can spend months and months and months and not end up with any improvement at all. And the third one is having that intuition from the beginning of project of trying to figure out what the future numbers will be without running the TDM model. So that helps to build our engineering judgment, which is needed a lot in traffic volume forecasting, and then it helps to correct a lot of mistakes which are associated with final numbers. Is kind of wanted to share our lesson learned. So thank you for being a part of this long journey, and very exciting journey called travel demand modeling. I hope we have given enough information to work on actual travel demand model projects. If you ever encounter any issues or want to discuss some ideas, we can discuss, and you can send a message to any of the authors, and we would be happy to help. Thank you very much for joining in, and in the next chapter, we will look at another exciting topic which is emerging called highway safety. Thank you very much.